Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 34, and the previous video to this I discussed the two-state paramagnet, and there are two videos on that. But the relevant video to this is number 23, where I discussed the multiplicity function for n molecules or n particles of an ideal gas. Alright, so what we're going to do here is talk about we're going to really derive the ideal gas law, but yeah, yes and no, I suppose we can derive the ideal gas law. But really what we're trying to do is as follows. We know that the spontaneous exchange of energy is governed by the temperature. We know that where the temperature is different between two bodies, they will exchange energy. So what happens about the spontaneous exchange of volume? What if the system can exchange volume as well as energy? Well, I'm going to tell you that that is governed by pressure. Now that should be intuitive enough to you, but we'll actually find out that that is the case from our study of thermodynamics. So let's go ahead and do this. If our system can exchange both energy and volume, that means that the entropy is a function of both energy and, we'll say U. Actually, I'm going to use the U and V. Okay, so when is it in equilibrium? It's in equilibrium when it's no longer changing. That means del S, we'll say take two systems A and B, and let's just look at U sub A. Well, we know that's equal to 0, and we also know that the del S del V sub A is equal to 0. Now this condition here we saw previously brought us to the equation that 1 over T is del S del U. That gave us that equation. So what will this particular equation give us? Del S del V sub A is equal to 0. Well, we know that the total entropy is just the sum of the individual entropies. That's just it's just a property of entropy. So that means del S del V sub A is equal to del SA del VA plus del SB del VB. But we know that if we add anything to A, well, we have to have taken it from B. So we'll say del VB is minus del VA and vice versa. So that means we can say that this is actually minus, sorry, that should have been A the whole time. Excuse me, I'll write it properly. There, that's what it should be. But we know that del VA is minus del VB. So we can do this. We can see from Biro we're going to write, and we can write it this way. Okay, we can write it this way. Okay, and that's going to be equal to 0, of course. So that means del S, I'm going to write it another Biro, that the change of entropy of A with respect to the volume in A is equal to the change of entropy in B with respect to the volume in B. Perfect. Okay, and that's of course at equilibrium. A strange and difficult word to pronounce, I find. Alright, so when we can exchange volume, we also have this particular expression for governs equilibrium. So from experience though, we know that two systems are in mechanical equilibrium when their pressures are equal. Now, mechanical equilibrium means the volumes aren't changing. So somehow this must be, it's likely that this is related to pressure. Let's look at the units of it. So we know the units of entropy are joules per Kelvin, and we know the units of volume are meters cubed. So what we're going to have is as follows. We're going to have del S del V is going to be joules, or well, it's going to be newtons per meter squared per Kelvin. So this here is going to be, if you put it down into its most basic format, if you look at it, right, we're going to have del S del V is going to be, well, entropy is joules per Kelvin. Okay, we know that volume is meters cubed. We know then the joule is force times distance and so on. We can work it the whole way out if you like, but basically we're going to get newtons per meter squared. Okay, and we're also going to get a per Kelvin. But so we know this here is force per unit area, that is pressure. So you have this per Kelvin, this extra per Kelvin term. So that makes us suggest the following equation. Pressure is T times del S del V holding U and N fixed. And you can't see that? Now you can. Okay? So, Right, now we've an expression for pressure, or we have an expression for pressure because of mechanical equilibrium, when the volume is no longer being exchanged. So let's see if we can somehow verify that this equation in actual fact works. And in so, I'm going to hopefully come up with a formula for the ideal gas law. So remember in the video where I discussed the multiplicity of an ideal gas, we had the multiplicity. The multiplicity is equal to a complicated function. I'm just going to call it f, but it's a function of n. And then we had v to the n, and we had u to the 3n over 2. Okay, so we need to get del s del v multiplied by t in order to get pressure. So let's go ahead and do that. Well, we're going to get that we'll say s is equal to k outside of n log v plus 3 over 2 n log u plus log f, like that. All right. Now we need to get the derivative with respect to u, but this isn't a function of u, and neither is this. So del s del u is very simply going to be equal to n k log v. Oh, sorry, it's not. It's going to be nk over v. What am I doing? Nk over v. And that means that P is going to be equal to T times del S del U is equal to T nk over V, or PV is equal to nkt, which is the ideal gas law. So it does seem that the expression we derived there, such that pressure is equal to temperature times del S del V, in actual fact is correct, holding of course the number of particles and the volume constant. Okay, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you enjoyed it you might also click on an ad. Thank you.